So in the last class, we derived the Saint-Bernard equation. Okay. So you remember Saint-Bernard equation was this: equal 0 on cross-sectional domain y on the boundary of cross-section. This is a well-known Saint-Bernard equation. So if we solve this Saint-Bernard equation, we can find out the warping function. Then we can calculate the stress, strain, and also stiffness of bar. Today I'd like to introduce a little bit different function. So Prandtl stress function. Prandtl stress function. So that stress function is this. This is defined. It's a function of y and g. So you remember we defined the cross section in y and g. Right? So Prandtl stress function defined by like a warping function. It's a function of cross section. And you remember the equilibrium equation for twisting problem and torsion problem is this: xg. This is a equilibrium equation. And then if we set stress xy equal g stress xg equal minus, then what happened? Let's put both equations into this equation. Then this equation is automatically satisfied. We are using this technique for the analysis of fluid, right? You know, potential of fluid or stream function. So to solve the potential fluid, we need to solve Laplace equation, right? This is Laplace equation, same thing, right? So to solve the Laplace equation, we are using this concept, okay? So you can think this is potential or stream function. So then stress xy equal gk minus g plus g. This is a result we calculate in the last class. gk y plus g minus y. Right? So here we have warping function and stress function. So here you can find out the relation between warping function and stress function. Okay? And then let's take the derivative of z again for first function. Then square become gk minus 1 plus yg. gk 1 plus k minus gk. k plus here, let me see, minus and minus. Right? Then let's sum both equations. Let's sum. If I sum this equation, y squared plus g equal here 0, 0 and minus 2gk. So we have a little different equation than Saint Bernard. This equation means local equilibrium equation. It derives from local equilibrium. So this should be satisfied in cross-sectional domain, right? So similarly, using the Prandtl stress function, we can derive some equation about the equilibrium equation on boundary. So let's look at the second equation here. So goal is to change the warping function into the stress function. So that equation becomes g plus y pi partial s g minus y plus y equals 0. And this part become 1 gk z pi from the relation here. Okay, from the relation here and here. So we are using the relation between stress function and warping function, and this part become minus gk 1 pi, right? Then let's look at here. Here partial g, here partial g, partial y, partial y. So finally, on the boundary, s plus on the boundary s equal 0 on boundary, right? So we can rewrite the carbon equation for twisting problem using stress function. So governing equation become finally governing equation become minus 2gk on n so actually here this equation mean equal arbitrary constant. So Prandtl stress function is a constant value on the boundary. So we can choose any arbitrary constant. So in mean we can choose just 0 on the boundary. So we rederive the governing equation. So we change the this is a governing equation for torsion problem using the stress function, right? Instead of using Saint Bernard equation. So Saint Bernard equation and this equation are exactly the same thing, but shape is different because we are using different function, right? So sometimes this stress function concept is useful. Sometimes the warping function concept is useful to solve the problem. It depending on the problem. Okay, then based on that stress function, let's find out very useful equation. So torsional moment M. This is a resultant stress can be calculated A on the cross section stress xg y minus stress xy g dA, right? We already know about this. This M is a torsional moment. So let's just torsion. Torsion can be calculated by integration of stress. And this become, let's put the Prandtl stress function, then become A, okay, and minus y minus g y g dA, right? Then let's use the integration by part. You know integration by part. So integration by part means, so here we can use the rule y equal y pi y minus pi, right? And also, this is a hold for also g, right? Then this equation become 2 a dA minus A G dA, right? So we can use same partial G YG minus, right? So you might think equation become a little bit complicated. So the moment can be calculated by integration of stress function and now we need to consider three terms. First term, second term, third term, right? Now let me think about the second term over there. Second term, A, Y, pi y, dA. How can I integrate this? This can be integrated by about G and Y. So Y pi y dy dg, right? So here we have a cross section. Here, let's say y, here g. So this equation means the internal integration means we are integrating some band. This is band. And this is the band dg. dg, right? We are integrating some band here, right? And this is this length is calculated from the internal integration, right? And we are changing the g. So, okay, then this equation become pi y y1 y2 dg. So this this equation give us the value at this point pi y at y2 here pi y at y1. The difference between both, right? So, but here we need to remember, here the stress function equals 0 on the boundary. At this point, at this and this point is your boundary, right? So, result of this is 0, right? And whole of this integration becomes 0. So we can do exactly same thing for third term here. So this becomes 0, this becomes 0. So finally we can calculate the moment very easily to integration stress function dA. we can calculate the moment very easily, right? Torsional moment. So to this point, you should remember, first, we introduce a special function. It's named Prandtl stress function, right? And based on that special function, we rederive the carbon equation. Okay? This is carbon equation, right? And then we calculate the torsional moment using that Prandtl stress function, and finally this equation gives us relation between how to calculate the torsional moment from the Prandtl stress function, right? Looks very simple. So all the procedure looks just complicated, but nothing. You can easily understand. So derivation procedure is not very important, okay? The concept is important. So you need to remember always all concept first, and then derivation. Okay, so I like to give you example. Example. Elliptical cross section. So let's consider elliptical cross section. So elliptical cross section looks like this. Okay. Y and G. This is A and B. So due to the carbon equation, here stress function should be 0 on the boundary, and in the cross section 2gk. This equation should be satisfied. Okay. Starting point of the solution is to assume the stress function. Okay? We can assume some stress function, right? Which satisfies the boundary condition. What kind of a function we can use? The easiest one is this one. Lambda A square plus B G B square G square minus 1. What's this? This is the equation for ellipse, right? So if you use this function satisfies phi equals 0. So we don't need to consider boundary condition, right? Because this function is already satisfied the boundary condition. And let's put this function into here. Then we can obtain the equation a squared 2 plus b squared 2 equal minus 2gk. Right? Here in this function, unknown is lambda. If you calculate lambda, we can find solution. So if we put this equation into here, we can find lambda. Lambda become minus a squared plus b squared a squared b squared gk. So now we find the solution for stress function because we find the lambda, right? This. And also, let's calculate the moment m equal minus 2g. It was just 2 minus 2. M2. It was 2 pi a dA. We can calculate this. If we calculate this, this become a squared plus b squared pi a3 b3 gk. And we can also find out the relation between lambda and moment. Lambda become minus pi ab m. So here we found the stress function for elliptical cross section, and we found the moment m. Right? So finally we can find the stress function pi equal minus pi AB M, right? A square y square plus b square c square minus 1. This is the final result. So when a specific moment m is applied, we can find out the stress function, and then we can calculate the stress distribution on the cross section, right? And also strain. We can calculate everything. And you remember there are relation between warping function and stress function, right? If you use that relation, we can calculate also warping function. So relation between warping function and stress function. So that relation was y plus g warping function. So how to calculate warping? Y plus equal gk over 1 xg minus g plus gk over 1 xy. This is relation between warping function and stress function. So if we use this equation, we can finally find out the warping function a square plus b square minus a square yg. This is warping function. Warping function gives us a distribution of the displacement in out of cross section, direction in out of cross section. So if we plot this, what happened? So y and g. So if y and g is plus this part, right? This part, okay, warp. So displacement happened in this direction. And how about this part? Also in this direction, negative direction. So these two parts, displacement is a positive x direction, these two parts, positive y direction. Right? So, how you can plot this, maybe. Then, I don't remember. How can I plot that? Then, x, y, maybe. Okay, so if we look at that equation, for the circle, A and B equal same, right? For the circle. If A and B is same, then it becomes circle, right? Circular cross section. So if A and B is same, what happens? Zero, no warping. No warping. So then in this case, warping becomes zero, no warping. No warping happens. Here, plus warping, plus, minus, minus. So, elliptic case and circular case is the easiest case for torsion problem, but for general case like rectangular cross section, it's very hard to calculate the warping function or stress function and also stress distribution. We need to use some numerical procedure. So, and then I give you some useful equation about torsion. Torsion of rectangular bar. This is rectangular. Y cross section is rectangular. G, A, B. When A equal B is same, it means square. Square cross section M torsion can equal 0.406 A 4 GK. This is a known solution. So long times ago, I think the Timoshenko calculated this. And really important special case is that B is much bigger than A. Then M equal 1/3 B A 3 GK. So this case means very thin case. This is a B, A. Very thin case. Thin word case. Thin word case like this. So here 1/3 B A cubic. The name of this equation is Brett formula. So J effective become B A 3. So here this Brett's formula is very important to calculate the torsional stiffness of open cross section. You remember? We know how to find the torsional stiffness of thin walled closed section, right? And now I like to talk about thin walled open section. So basic equation is that for the solution of thin walled open cross section. Thin walled open cross section. J effective equal I equal 1 to N 1/3 L I T I. So, for example, that equation means, so thin walled cross section consists of 3 plates, 3 thin wall. First wall, second wall, third wall, right? So stiffness of thin walled open cross section is just sum of stiffness of each wall. So this equation comes from Brett's formula here. Okay? Here J effective is B A cubic over 3. Right? This equation comes from that equation. So here this is a L1, L2, L3. Let's say, let me give one more here. L4. And thickness T1, T2, T3, T4. Here, this is opened here. It means here opened here, right? It's not open. So in this case, J effective become 4. So when the L1, L2, L3, L4 are same, L, and T is all the same T, plus 3 over L T square, 4, 3 L T square. When Li equal L, Ti equal T, right? So for the closed section beam, it's very, very easy to calculate the stiffness, right? Very easy. And let's compare the result with the thin walled closed cross sections. J effective calculate by 4A square TDS. You remember? TDS. Okay, so this is a same dimension but closed case. L, T, right? Only difference is the same amount of material, right? Only difference is in open cross section, this part is cut. But in this case, cross section is continuous, closed, right? Very small difference, right? Then let's calculate the J effective. For J effective become 4L, 4LT, become TL4. Let's compare this and this. So stiffness ratio open, closed, equal T square. Which one is more steeper? Which one, open or closed? Open or closed? Which one is steeper? 정호? Closed. Much more steeper. Ratio is like this. Square, T over L, square. For example, L equal 1 meter. T equal 0.1 meter, so 1 centi. Then cross section is much, that ratio become 3, 4, okay, 100 square. So 0.75, okay, 10. Very, much effective, right? So it's very important to know that. So yeah, for example, let's say here we have tank ship. This is a cross section of ship. So usually some ship has a cross section with an open cross section. Some ship has a open or closed. So some tanker ship here we have a liquid tank. So, but some we have this kind of ship cross section. For what kind of ship? Container ship, because we need to put into the container inside. So in this kind of ship, torsional stiffness is very small, so that become a problem. Okay. Thanks. So today I like to finish the study about the torsion and warping, twisting. Okay.